let's say of an inch, the actual x should be 1, but I have a positive error in that. So now I have to calculate the function value at 1.11 minus what the function value should have been. And I get a number. And that is the actual error in the function that I created by having an error in x. So all I have to do is just plug in the function in the graphing calculator, clear everything else. Don't do this by hand, please. Enter x squared plus 2x and just evaluate. Second in table, I'm evaluating at 1.11, and I'm evaluating at 1, and I'm done. So this is 3.4521 minus 3. So the actual error is 0.4521. If we come back just to our discussion with the disk, I have a 0.11 of an inch error in the radius of the disk. This is not the formula for the radius. I'm just explaining. So I have this error that I created, and that triggered an error in the function. The error in the function, this is just algebra, right? We didn't do any calculus here. The error in the function is the function value with the error minus the function value that should have not have the error, the actual that we should have gotten. And this is the error triggered in this particular function by this error created in x. Of course, this is not what we really want to do. What we really want to do is we want to approximate. Delta y with dy. And the question is, what is this? What is dy? We have not seen dy before. We've seen dy over dt or dy over dx, but we've never seen dy by itself before. What am I saying here? Here's what I'm saying. Give me a function, please. Any simple function that you can think of. Can anyone give us a function? A simple function, something that you can think of?
Do x squared plus 3x plus 1.
Very good. So we have this function. Can anyone give us the derivative of this function?
(2x plus 3).
Excellent. Now, what is this? It's that, the differential. So remember we had dy over dx being the same with f prime of x. I always mentioned that we have different notations for the first derivative and for all derivatives, but for first derivative that we are discussing right now. So if we cross multiply or just multiply both sides by dx, we get dy equals f prime of x dx. This is what we call the differential. It's not the derivative. It's the derivative multiplied by delta x, and dx mean the same thing. The error in x. So if that's the case, then dy will be the same thing, but in parentheses and multiplied by dx. So please understand that these are not the same thing. The derivative of the function and the differential of the function are different. Now, why am I making such a big fuss out of this? Because chapter 4 is based on this concept. Okay, so let's try another function. Let me make up one. So let's say f of x equals 3 e to 2x plus x to the fourth. I would like us to find f prime, which is the derivative. And I would like us to find dy, which is the differential of the function. How was the differential determined? From this relationship, we multiplied both sides by dx. So dy equals f prime of x dx. Can anyone differentiate this function for us? Maybe let's make it even more interesting. Natural log of x squared. A good review of the formulas. No products, no ratios, but a good.
Is it 2x times?
So it's 3. E to a function prime is e to a function times the inner function prime. So I'm hoping you want to say 6e to 2x. So it's 3. E to the function prime is e to the function times the inner function prime, which is 2. So 2 times 3 is 6e to 2x. Is that okay? Is that okay? Plus.
Or x to the third.
Good. Plus, remember natural 1 over
2x.
1 over x squared times the inner function prime.
Which is divided over dx. How?
The inner function prime is 2x. I will simplify. So the final form for f prime is 6e to 2x plus 4x to the third plus 2 over x. Everything is done. How do I write the differential now?
Just multiply that by dx.
Exactly. It's the whole thing multiplied by dx. I don't have to do anything else. I just have to copy this in here. 6e to 2x plus 4x to the third plus 2 over x. This is it. What's the big deal with dy? Don't we just have enough? I have delta y. Why do I need dy? I already have the exact. Well, delta y is approximately dy. If I can live with a little bit of error, I prefer dy because it's easier to calculate. This is not that easy to calculate. So coming back to this example that we just created. So we had f of x equals x squared plus 2x, and we found that delta y was 0.4521 after all these calculations. Now, can anyone give us dy, the differential of this function? Can anyone give us the differential of this function? Not the derivative, the differential.
Is it 2x plus 2 times 0.4521?
Careful, this is something else. This is dx. So now I want to calculate dy to see how close it is to the actual error. So this is an approximation of this. Let's see how close it is. So dy will be 2 times x plus 2 So this is 4 times dx, which is 0.11. I don't even have to use a calculator. Here I needed to determine this. I need to plug in the graphing calculator. I need to determine this. Then I had to subtract, and I got this. With dy, I have 0.44. Are they close? Very close. Why? Because the actual exact error, which is this, can be approximated by the differential of the function. Here's the differential, here's the actual. We will be asked to determine both. Okay, so let's look at an example. Okay, and this is section 3.6. We're going back. 3.6. Remember, 3.7 is not part of the class. Okay, page 341. I have not taught at a candle light or flashlight before. This is interesting. Okay, so find delta y for x and delta x values given. Find dy, which we know it's f prime of x dx. And find dy for the given x, exactly what we just did. They want us to find the exact, which is delta y. They want us to find the approximate of delta y, which is dy, for the given values. So let's choose a problem. Anybody, please? Okay, I will choose 9. So we have f of x equals e to the x equals 3, delta x equals 0.1, and delta x and dx are always the same. Delta x, this is the so-called differential of x, like delta y is the differential of y. So they want us to find delta y. Well, delta y by definition is f of x plus delta x minus f of x. X is 3, delta x is 0.1, 3 plus 0.1 is f of 3.1 minus f of 3. I can calculate this by hand. I have to put in the calculator. In a moment we will. Can anyone calculate the differential of the function for us? Can anyone give us a differential for e to the x? Assuming that this light is not too bright so you can see here. Can anyone give us dy, not the derivative, but dy for this function? Anybody, please. Anybody, please?
Is it e to the power of x, and then times that 0.1
Times dx.
d of x?
Of course. So this will be e to the third, because x is 3, multiplied by dx, which is 0.1. And we want to see and convince ourselves that these two numbers are very close to each other. They have to be. Good. So we have just e to 3.1, e to power 3.1 minus e to the third power. Good. Oh, oops. Good. So this is f of 3.1 minus f of 3. And now let's see what we get with the differential. E to the third multiplied by 0.1. So the first one is 2.112 and the other one is 2.0085 or 985. Let me copy 4 digits. So the actual difference is this. And what we are getting is, if I want to round up to the hundredth, then I have 2.01. Okay. Do we need to work on another problem? Let's take a look. Do we need to choose another to illustrate how to determine delta y and dy?
Can we do number 6?
Yes, of course. Number 6. Let's take a look. Number 6, we have f of x equals 1 over x squared. X equals 1. And delta x is 0.5, which is always equal to dx. Delta x and dx are identical. Why do we use 2 different notations? Because when we use delta y, we want to keep the notation delta x. When we use dy, we want to keep the notation dx. That's the only reason. But they are absolutely identical, always. Perfect. So delta y will be f of x plus delta x minus f of x. X is 1, delta x is 0.5. So we want f of 1.5 minus f of 1. And this is just algebra. There is no calculus here. So we're going to put those in and find the difference. Now, before we do that, can anyone give us the derivative, the differential of dy, of the function 1 over x squared? What is the differential? Remember, when we differentiate this, we have to change it into x to negative 2. So let's differentiate x to negative 2. Can anyone differentiate x to negative 2, please? Anybody, please?
Is it negative 2 over x to the third?
Yes. Times? Because that's not the derivative.
Is it just dx?
Exactly. Exactly. So dy is f prime of x times dx. Excellent. So negative 2 over x is 1. I'm going to just put 1 to the third power, multiplied by 0.5. See how easy this is to calculate? So this is negative 1. Done. But here I have to use the calculator. When I do the algebra, I have to use the calculator on 1.5. But here, -2 over x to the third, which is 1, multiplied by dx, which is 0.5. When I multiply these two with a minus, I get -1. But yes, this is an approximation of the actual. I agree. So now let's see what we get. So I will put in the graphing calculator 1 over x squared. So 1 divided by x squared. And then second table. And I will plug in 1.5. And when I plug in 1, I get 1. So the answer is 0.4444 minus 1. Any questions? Any questions on how we calculate these? The dx is given to us, the function is given to us, and all we have to do is determine the actual and determine the approximation. So 0.5556. Any questions? The last thing that I wanted to mention, and I'll mention it again after the spring break, is the fact that here's a function, here's a point P. Now, near P, let's say P has the x-coordinate A. And let's put it in a coordinate system. Very close to A, I can approximate this function using the equation of the tangent line at that point. If you remember, we've done this semester so many times. Find the equation of the tangent line, find the equation of the tangent line, find the equation of the tangent line. And here's the reason why. This line, it's called the linear approximation of the function near A, not here. Here is too far. I need another equation, another tangent, but very close to A, left and right. It doesn't matter that much if I use the function to evaluate or if I use the equation of the tangent to evaluate the function. So I'm just going to give a very simple example and I'll stop. So find the linearization L of x of the function x squared at x where a equals 3. So this is 19, f of x equals x squared, and they want us to find that a equals 3. So the equation of the tangent line, L of x, is f of a plus f prime of a, x minus a. When I have light hopefully next Monday after the spring break, I'll show you how we get to this formula. All I have to do is plug it in. What is f of a? It's f of 3. 3 squared is 9. What is x minus a? Exactly what I see, x minus 3. What is f prime of a? I don't know, I have to find f prime first. Can anyone give us the derivative of x squared? And then we'll plug in a, which is 3. A is 3.
2x.
Yes. So when I plug in, f prime of 3 will be 6. I'm done. I found the equation of the tangent line to the graph of the given function and the given value of a. that will approximate the function only near A, only like 2.9 or 3.1. So what is this? So it's a linear function, 9 plus 6 times x minus 3. 9 plus 6 times x minus 3. I distribute 6x minus 18 plus 9 is minus 9. So what I'm saying, and this is it, this function can be approximated by this line only near x equals 3. Nowhere else. So I'm saying if you don't want to evaluate, if you can live with a little bit of error, and you don't want to evaluate this function at 2.9, you can evaluate the line at 2.9 and you'll be very close. Why? Because this equation approximates the function very, very close to A.